So you can see my screen?
Yes.
Yes.
Okay, perfect. Okay, if you remember last time we talked during class about the policies, basically, big part of it, the course policy, and then we started talking about network communication. We mentioned about network layering, then we talk about remote procedure calls and how basically that's common. It's a common thing that we do in a distributed systems, right? Using, of course, for a distributed system, we need network communication. We define it, if you remember, as like a set of computers, let's say, basically connected through the network and doing a certain task collaboratively all together. So today we're going to talk about time, just purely about time and why that's so important. When we are talking about distributed system, why timing is very important and why it's so challenging. And yeah, about why it's so challenging talking about time. So basically what I'm going to cover is the need for time synchronization. Then I'm going to talk about wall clock synchronization. Then I'm going to talk about logical time or Lamport clocks. So imagine this scenario. We have a distributed edit compile workflow. So you're writing your program, let's say in this example, a C program in your editor, which is another computer, and you're compiling it through a remote procedure call using a compiler that exists in different computer. So here you can see like the time, the local clock in each computers, okay? And let's say due to the clock drift, the computers are not totally in the same timestamp, okay? They don't have exactly the same. The clock is drifted in one of them or in either of them. So in this just basic example, when you try to run like your program using the compiler, if the times are not synchronized between the editor and the compiler, because we are assuming they are in two different systems, so you're going to face problems. For example, your output O is in the object file for the output basically the object file, which contains the machine code produced by your C compilers is having this timestamp, and the compiler itself that generate the C file is having these timestamps. So if you try to call the make to basically generate a, let's say, executive files, you're not gonna, basically your command not going to run, because you're going to see like object file mismatch, because these two computers are not exactly synchronized. So before I jump into this and say why that can happen, okay, I want to talk, or I want to show you this video which talks about why time is important, okay? How basically we measure time. And can you still see my screen?
Yes.
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 Yeah.
Okay, what's happening? I can't see you, that's the thing. I'm sorry, let me see what's happening here. Because I cannot see you, it's disappeared. Channels. Okay. Okay, so please let me know if you're hearing the sound.
Yep.
Yes.
In some sense, this everyday watch isn't special at all. I mean, I bought it for $10 at Target. Yet once we look inside, it's amazing. Let me show you. I'd call it the key machine of the modern industrial age. Precise timekeeping made possible things like the global positioning system and our telecommunications
I'm sorry.
infrastructure. Now, this metal container holds the heart of this watch. Inside lies a tiny quartz tuning fork. I have one. Now, it's so tiny that I keep it in this white cap. You can see it right there in the center. Now, although this modern circuitry is vital to the watch, it's based on the same principles of the first clocks built in the 17th century, resonant motion. It's easiest seen in the pendulum clock. This family heirloom, it hung in the living room when I was a kid, uses the motion of a pendulum to keep time. Now, this pendulum oscillates with a regular period that runs a clockwork that translates this motion into movement of the hands. There are many ways to create resonant motion. For example, a tuning fork. This one vibrates 440 times a second. That's an A note when struck. I love that sound. Now, if I slow down the motion of the fork, you can see how the tines move back and forth with a regular period. That's resonant motion, like the pendulum, which can be used to measure time. The quartz crystal I showed from inside this watch is a tiny tuning fork. It vibrates at about 30,000 times per second. But how do you get it to vibrate, and how do you measure its vibrations or record its vibrations? I mean, we cannot get a hammer in there to hit the quartz crystal. The engineer who designed this digital watch used something known as the piezoelectric effect to make the small tuning fork vibrate. You can see this piezoelectric effect most easily with Rochelle salt. Here at the center lies the crystal. I've attached 2 electrodes made of tinfoil and strung wire from them to a small bulb. Watch what happens as I strike the crystal with a hammer. As I deform the crystal, it generates a current. The reverse also happens. If you place a voltage across the crystal, it deforms. This is how the quartz tuning fork in the watch is pinged. A voltage from the battery sets it in motion, and then the watch's circuitry measures the current fluctuations that represent the resonant motions of the tines. Quartz is ideal for digital watches because of its outstanding physical hardness and mechanical and chemical stability. And that stability makes this watch work nearly anywhere on Earth and under all but the most extreme conditions. One more interesting thing about these digital watches is how these tiny tuning forks are made. On a production line, engineers must make these quartz tuning forks so accurate that they vibrate at 32,768 times a second, plus or minus 1/600th, about 2 parts per million in frequency. If that frequency differs by 1/600th, the watch will be off by more than 1 minute a year. And to see how they tune these forks, look at the ends. You see deposits of gold at the ends of the tines. These are added to make the fork's vibrational frequency too low. On the production line, a laser zaps tiny bits of the gold off until the frequency of vibration is just right. It's a wonder that these magnificent engineered objects are so inexpensive. I'm Bill Hammack, the engineer guy.
Okay. Could you hear? So now we have a better idea how we are measuring the clock or the time in our local systems. Let's say in our digital watch or even in a computer. In computer, it would be a slightly different story, okay? When you're connecting using our laptop or smartphones or tablets, it's a slight story that we're going to talk about. But now you have an idea about how the clock works and why basically, okay, let's answer this question. What makes time synchronization hard? Why having 2 computers completely synchronized is very hard? Go ahead.
Okay, because it's not deterministic, like the time that it takes to communicate between 2 machines, for example. Like they can have like different like physical things that delay the communication.
Okay. True. But that's it can be. I just see there's some students they couldn't see the video. I'm going to include this. Anyway, the videos are inside the slides. The next one, I just put the link. So if you have problems seeing it here, you can just see it in your local system. Thank you, Paul. But let's talk about it. Why it's a hard task giving to computer things. So you heard about that we are using quartz in order to, quartz oscillations in order to measure the time. And quad oscillators are sensitive to temperature, age, vibration, and radiation. In the video, you see the guy is heating the clock. I mean, you can, of course, you can hit the clock in your table and there's nothing happens, but those small shocks or like a small vibration going to drift the clock slowly. It's a matter of time, okay? But it doesn't matter, even the clock in your hand or like taking out, throwing it away, it's going to cause a slight drift during the time. So that's why the accuracy circle is 1 part per million, basically 1 second of clock drifts over 12 days. That's like normal clock drift for an quartz oscillators type watch or clocks. But when we are using also internet, the internet is asynchronous. You know that we have this message delay, that arbitrary message delays when you're communicating. Because in our system, we are not necessarily, in our system, like our computers can get synchronized by the time servers, right? By the time servers can synchronize my computer automatically. I don't need to have an internal clock necessarily. And so because the internet is asynchronous and also it's a best effort, which means messages are not necessarily always arrive. There are some missing packets through the internet. So for these reasons, in general, having to clock in 2 different systems completely synchronized is very hard. When I'm talking about synchronization here, I'm not talking about minutes or hour or second. We're going to like more like millisecond, let's say, in some cases, even nanosecond drift is an issue in for ourselves. So, okay, now we talk about the need for time synchronization. It's very important. When we are talking about distributed system, we're going to talk about this more. So let's talk about now how we do that, how we try to synchronize 2 different systems. And I'm going to talk about Christian's algorithms, Berkeley algorithm, and NTP. So why don't we just use coordinated universal time or UTC? Because you know UTC is broadcast from radio station on land and satellites. For example, we have a global positioning system that your phone and your smartwatch or your tablet, they are getting synchronized with all the times. Because they have this GPS connection, they can get synchronized by these GPS systems. Because the GPS system is constantly broadcasting UTC signals. So also computers will, receivers can synchronize their clocks with these time signals. If you maybe, I said we have time servers, I'm going to talk about that. And also we have signal from land-based stations that are accurate about like 0.1 to 10 milliseconds, because we have some station like ground-based station that they also, they also broadcast UTC times, so different stations can get synchronized with them. So when we're talking about GPS, GPS is the almost, I mean, for a consumer-based, GPS is the most accurate one. And it's about 1 microsecond. The drift can be 1 microsecond. So I'm telling you what, GPS is very accurate. So there might be this question why we don't use GPS if that's so accurate. If we can solve the problem of time synchronization up to a microseconds, why don't we use GPS in our computer? Nice question.
To my understanding, is because GPS is so expensive.
It's true. Yeah, exactly. GPS is expensive relatively. I mean, it's getting cheaper, but it's still relatively expensive. And another issue is GPS is not working very accurately indoor, right? It's still, we cannot use like GPS at the moment. We cannot use GPS for indoor localizations. We have different methods, but we are not using GPS for indoor localization. So my computer, my laptop, sitting in my desktop, cannot synchronize using GPS, the clocks. And also, of course, the price of the devices. It's not, how to say, it's not cost effective to have all the devices equipped with GPS. So that's why basically we cannot use GPS. We need other type of mechanism to have this synchronization. So before I go, I mean, there is another funny things here. Why we call coordinated universal time UTC, not CUT? Anyone has any idea? So when they wanted to come up with the standard, basically English-speaking countries, they were saying, okay, let's put it CUT, coordinated universal time. That's how we say it. And French speakers, they were wanted to have it temp universal coordinate. That's why they couldn't get angry on it, and they said, okay, let's put it UTC, not CUT, not TUC, UTC. I mean, that's a simple naming changed. Okay, basically it's a universal time. At least it started with universal time. So now you know the story. Sometimes that silly things change. Okay. So how we can synchronize to a time server? I said we have a time server. Let's say we have a time server like in my city. Okay, as an example. And this time server gets synchronized using a GPS or using a radio station that broadcasts UTC signals. So I'm a client, I have this time server. So I can ask the time of the day during an RPC packets, right? Okay, I'm asking what is the time of the day? And the server asks me, this is the time of the day, okay? So what is the issue with this? With this
the time that it takes to receive the message? Maybe?
Exactly, the time that takes, basically the round trip times that takes for the message to arrive to the server and for the server message to arrive to you, right? Or basically you can say the time that this, the server replies, comes and receives to you, because there is a delay, right? So it doesn't work, this method, okay, because at the end, no matter what, you're going to get outdated packets from the time server. So there is this proposal called Christian's algorithms. So this is the outline of this. I'm going to talk about it. So you have the client, you have the time server. So you send the request packets for the time, okay, in your T1, and you include the T1 in your packet. You include that I'm sending this packet, I'm asking you this time in this time slot, local time slot. The server can receive this T1. Then the server, of course, receive these packets in the T2. And the server for the reply message include the T2, the time that it received the packets and the time that is sending the packets. Include this information in the response packet and send that to the client. So client going to receive that in T4, right? Because again, there is a slight delay here. So client will receive the message in T2. You remember this is like, if you say this T3, there is this delay right here. So how we can calculate the time now, accurate time? What we need to know here? Of course, if I know this, right? If I know this exact delay, I can just look at the T3, right? And add it with this delay and come up with the T4, right? So in order to do that, we need this T3 time that we have in the response message, and we need to calculate this value, sigma response, or let's say the delay that it takes for the message to arrive from the server to the client. So, but we don't know this, right? This is not a common knowledge for us. We don't know. What we can calculate is basically the round trip times, how much the times it took for our message to receive to the server and for the server message to receive to us. So basically what we can calculate this value. Because we have all these are known values. We have T4, because I know when I'm receiving the message, because this is the local time. I'm not yet synchronized. I just look at my clock and I record the T4. I have T4, I have T1. This is the common knowledge for me because this is my local time. And in the message that I receive, I have T3 and T2, right? This is the message, this is the information I'm receiving in this packet. So based on this, I can calculate the sigma, or let's say the round trip times. Is it clear? So I can calculate this to, so for this reason, then I don't know this in particular. I know the summation of these two, and not necessarily these two are equal, because sometimes for this message might take more time to arrive to the server than for the server message to arrive to you, because the packet's taking different routes in the internet. So for that reason, how we can calculate that? We can assume this, the time, this basically these two sigma are equal. So if I consider this, then I can calculate what time I need to synchronize with. Is it clear? Anyone got lost here? So the whole idea here is just calculate the round trip times, okay, to simplify it. Just calculate the round trip times, divide it by half, okay, and use this T3 from the time server, add this half of the round trip times to it, and that would be the time that you need to synchronize with. You need to adjust your clock with that time, okay? So don't get confused. We have a client that has, of course, local timing, but the client wants to make sure that its clock is synchronized, is like updated, because we know the clock can drift by passage of the time. So client receive this message, can calculate this value and update its own clock, its own local clock. So that's basically Christian's algorithms. So let's start. Yes, go ahead, Anthony.
Is that the formula, considering that, well, it's taking like the same amount of time to send the request than to receiving the response? Is that why it's dividing it by 2? I mean, it's symmetrical?
Of course, it's not accurate. Again, I mentioned it's not accurate, but there is no other way that we can know this value.
Okay.
I mean, there is literally no way you can calculate this value.
Okay, all right.
because of course you're receiving the packet. The packet has this information when it's sent, okay? But you know your local time is drifted, okay? So you cannot necessarily, I mean, you're trying to synchronize. That's why you're not so sure about your own clock. You're not relying on the local clock at all. That's why, I mean, there is no other way. I mean, there is literally no way you can calculate this value precisely. That's why you can calculate all these times, and then you can get the average, and that's the best you can do using this method.
Can you do an example with actual like times, just to understand it better?
Yeah, I think I can do that. If we say like T time is like in a time 1 I'm sending, okay? So T2, let's say it's 2. I'm just simplifying it, okay? So, I mean, let's say T3 take another value is like 3, okay? So it's the second 3. So this is the local time for me. I'm sending in the first second. Then I receive this T4, let's say in, let's make it more complicated, 3.6, okay? For my local time, okay? So then I can put this value here and calculate how much it took, okay? So basically what I can do, I diffract this 2, I get 2.6, okay? 2.6 I get from here, then I diffract it from the difference between these two, which is 1 second. I have this value already here, right? This is included for me. So this is minus 1, I get like 1.6. Then I divide it by 2. Then I get like 0.8, right? So, so what I can say here, I can say this is like 0.8, let's say, second delay. So now I have the T tree, I have this tree, then I'm going to synchronize my time to 3.8. Is it clear? So I received, I mean, T4 for me was 3.6, okay. But when I receive it, now I need to set my clock to 3.8, okay? Because I know my clock is drift. This is the accurate timing. This is the only accurate timing I have. I cannot rely on my local clock. But just based on that, I can at least calculate the round trip times. At least I try to calculate round trip times and then get this value. Is that clear? I mean, it's very simplified, but at least it can give us some idea how it works. For
But
example,
if the value that you got is 0.8, how do
okay.
you go from 3.6 to 3.8?
Okay, that's a very good question. I'm going to talk about it. Basically, what happens in the local systems, you don't simply change your clock from 3.6. Let's say you just jump like to 0.2 seconds forward your clock. What you do, basically, you increase that, you increase your, how can I say? You try to cover this 0.2 difference gradually, okay, during the time. So for example, during like 2 minutes, you try to cover that 0.2 seconds. The times never change suddenly. It changed gradually for the local system. Because at the end, you don't want to mess up with your local process that is happening, right? So what you can do, you can like increase the, let's say, frequency of your, I don't know, like, how can I say? For example, about the clock that we were talking about oscillators, you can increase that frequency in order to recover this delay that you are behind gradually. I'm going to talk about it. That's because a valid question. I mean, cannot just simply change the clock in a, let's say, in a system, because that's going to mess up with the local process that are continuously happening in the systems.
So it's more like an approximation or estimation, right?
Yeah, that would be an estimation that we need to cover. I mean, so basically, I know that now my clock has like 0.2 second drift. I need to recover that.
Do you know how old is the Christian's algorithm?
Pardon?
How old is the Christian's algorithm?
No, not so sure. I'm not sure really.
I'm just asking the question because probably, you know, that we are dealing with, you just use the example of on seconds, but we are dealing with milliseconds or probably just, you know, less than that. And I'm just wondering with nowadays bandwidth.
I mean, anyway, if I'm not mistaken, that it should be belong to computer. I mean, internet era. So I would say like it shouldn't be more than like 30 years old. I'm not sure exactly. I mean, to be honest, I don't know.
31.
31?
Yeah.
Okay, 31. My estimation was just 1 year, 30 years, 31 years. Perfect. Thank you, Teja. So let's talk about now the second proposal, how we can do that using Berkeley algorithm. So then people come up and say like a single time server can fail, and then you can, so that failure can block timekeeping. So you cannot just rely on the single time server and say, okay, I want to synchronize with this single time server. So especially in this course is about distributed systems. So what about a distributed way to calculate the time? So then these Berkeley algorithms come in play, which is a distributed algorithm for timekeeping. So there is this assumptions in this algorithm that I need to talk. So we assume all machines have equally accurate local clocks. So in this Berkeley algorithm, we are not relying on a time server. We are like, let's say like there are 5 systems. We want to like collaboratively come up with a timestamp. Okay, we want to set our time together. So what we are assuming, we have equally accurate local clocks. There is no one system has better clocks than others. And also we assume no machine has an accurate time source. Okay, not that any of them are connected to a like, time server. So what we can do is so simple. We obtain average from participating computers and synchronize clock to the average. I mean, it can't be more simple than that. So let's say in this systems, in this computer, so let's say this is a master computer. It doesn't mean the master has a better clock, or it's just a computer that initiates the algorithms in order to come up with the synchronized clocking. So in this example, you can see this is the local clock. Here is 3, here is 250, here is 325. Simplified again. Okay. So the master going to pull other machines' local time using the Christian's algorithms. So I'm going to pull all these times using these algorithms, using the algorithm that we already talked. So when I pull all those clocks, I get this response. So here is 0 because it's my local time. Here I get -10. Here I get +25. Then I get the average. The average will be like 5. Like we have +15. If you get the average, you get +5. So that +5 should be basically the time. Basically, times will be +5. So this will be like 3. Let's say 3 hours 5 minutes. Okay, and that would be the time all the clocks need to synchronize with. Is that clear?
It is, but I have a question.
Sure.
Well, I guess that this works to synchronize all the systems, right? But for example, if your program, your application relies on timestamp for some reason, this one, it's not the right way to get accurate time, right? It's more like to sync up all the system. And
exactly. This works like more like a setup computer wants to synchronize together, right? Mm-hmm. Not necessarily having the latest time or like accurate time of the day, or like a wall clock time. Mm-hmm. That's what we call it, like wall clock time. It's, I mean, but if you consider all of them having a time, of course they have a like wall clock time internally, right? So let's say I have my computer totally disconnected from internet with my 5 other computers in my house. Okay, they're totally disconnected from internet. They have the local clock already. Of course, it is drifted. I mean, each one has different, slightly. I mean, again, I'm saying difference. We are talking about millisecond, microsecond. Like it can be like nanoseconds. Okay, that's very, very powerful. I mean, possible. It's not something weird I'm talking about. So in those differences, then if I say, okay, I got all these 5 systems that their clock is already drifted, if I get the average of that, I'm going to get more or less very closer to the actual real-time clock. I mean, it won't be exactly the same, but it would be much better than relying on one systems. Right? It's, I mean, any questions so far? No? So let's continue talking about other method. NTP or network time protocols. And let's say how it actually happens. Basically, these are not what, or you never heard, but I assume you heard about NTP, network time protocol. That's what we are using in real life, okay? So for this reason, I'm gonna share with you this video. Let me see, how can I do that? I'm going to send you the link if you have problem listening it here. So please, you can watch it locally. I'm going to play anyway. Okay. I need different type of sharing. Sorry, that's why I'm stopping, because I need to do this here.
Hi, Dom here. Now, you've probably heard of atomic clocks. If you haven't, then it's probably about time you did. Atomic clocks have many uses within scientific studies, for example at CERN, where incredible precision is needed to sync their atom-smashing instruments. But atomic clocks are also used within the world we experience every day, including the internet, where exact timings are critical. However, they are probably most commonly known for their use within the Global Positioning System, or GPS. For a GPS satellite to work out your precise position, the timings of the signals it sends and receives have to be just right. The signals travel at the speed of light, which means an error of even a single microsecond in timing translates to an error of 300 meters on the ground. The timing has to be so well controlled that even tiny effects because of relativity need to be tracked. If we didn't know Einstein's equations, GPS wouldn't work. To keep precise time, GPS satellites carry atomic clocks. The more accurate the clock is, the better GPS can calculate your location. But how do they work? Well, at the heart of any clock is a frequency reference, an object that oscillates at a constant rate. In olden days, a pendulum was the frequency reference. One swing of the pendulum equaled 1 second. But pendulums are prone to manufacturing errors and fall victim to changes in temperature and gravity. So all in all, pendulum clocks are not so great for keeping accurate time. In 1927, the quartz clock was invented, a major leap forward for timekeeping. Quartz, or silicon dioxide, is a crystal with some special properties. When jolted with electricity, the quartz resonates or vibrates at very precise frequencies. Many materials can be formed into plates that will resonate, but quartz has an exceptional trick up its sleeve. It is also what is known as a piezoelectric material. When a quartz crystal is subject to mechanical stress, such as bending or hitting, it produces an electrical charge. So as it resonates, it generates pulses that keep time like the swinging of a pendulum. Quartz clocks are still used in all sorts of devices today, including watches, mobile phones, computers, oven timers, and even pacemakers, with about 2 billion quartz oscillators sold every year. Shaped like a tiny tuning fork, the quartz oscillators are standardized and designed to vibrate at 32,768 times per second. But this frequency alters very slightly due to temperature and pressure changes, and so, like a pendulum, over time they still lose, well, time. So in order to make the super accurate atomic clocks used today, a new strategy was needed. Physicists knew that atoms oscillated at very high and very specific rate. Not only that, but atoms from the same element will oscillate at exactly the same rate. Virtually immune to environmental factors and with manufacturing errors being irrelevant, atoms seem like the perfect oscillator. In 1967, the standard was decided and a second was officially defined as 9,192,631,770 oscillations of a cesium-133 atom. This number is what's called its resonant frequency. By bombarding a cesium atom with radio waves tuned to that exact same frequency, the cesium will resonate, absorbing some of that energy and changing to a higher energy state, a bit like an opera singer smashing a glass with a high note. The idea was to use this change in energy state to indicate that the radio wave frequency was exactly right. Let me explain. They kept the quartz from before as it is still a very good oscillator, but instead used its resonance and the electrical pulses it produces to determine the frequency of a radio transmitter. Radio wave frequency is measured in hertz or waves per second. Like counting the number of electrical pulses in a quartz clock, we can now count the number of radio waves to determine when a second has passed. So for example, if we know that a piece of quartz resonates at 32,768 times per second, then the radio transmitter will transmit a frequency of 32,768 hertz. When we've counted the same number of waves, then we know that a second has passed. Keeping this frequency exactly the same, though, is very difficult, because as we know, quartz changes its frequency due to environmental factors, and so in turn this alters the radio wave frequency. This is where the cesium comes in. Like I said before, when a cesium atom resonates, it absorbs some of the energy from the radio waves and changes to a higher energy state. These higher energy state cesium atoms are detected after they've passed through the radio waves. If the radio wave frequency is exact, then the higher energy cesium atoms continue to flow into the detector at their peak rate. If the frequency isn't quite right, then fewer detections are made, so another jolt of electricity is sent to the quartz oscillator, altering the frequency so it's just right to make those cesium atoms start resonating again, just like tuning a radio. This method of feeding output information back in is called a feedback loop, and basically means the atomic clock is self-adjusting. Unbelievable. And a fun fact. The National Institute of Standards and Technology, or NIST, in the US, has an atomic clock that is now so precise that if one of these had been running since the Big Bang, it would now be less than a second off. Wow. Thanks for watching. I've been Dom, and you've been watching everything.
Okay. Let me do the sharing again. So now you know how the how the clock works and how we measure basically accurate timing for the GPS device. As you heard, a millisecond mistakes in the clock can be translated to 300 meters on the ground. Okay, so that's why, I mean, not just for that reason, timing is very important. Having it, being able to measure accurate times. So, any questions so far? Okay, let's continue then. So, how this works, Network Time Protocol, or NTP? It enables client to accurately synchronize to UTC despite message delays, and it provides reliable services. It's survived lengthy losses of connectivity, communication over redundant network, because it communicates over redundant network paths. That's why it's a reliable service. And also it's provide an accurate service. Unlike the Christian's algorithms, it leverages heterogeneous accuracy in the clock. And how it happens is basically, okay, the server and time sources are arranged in layers, or we call that stratum. A stratum is basically, I mean, just the word means that the layer of series of layers of rock. That's what means a stratum. So basically, the servers are categorized in different layers. So layer 0 is the high precision time sources themselves, or basically those servers that are equipped with the atomic clock, or basically those servers that are equipped themselves with atomic clock. They are sitting in layer 0. And layer 1 is NTP servers directly connected to these servers. Layer 2 are the NTP servers that are synchronized with the stratum 1s, or with these servers that are connected directly with this one. So you can see it's like it's a series of basically layers that each one get its time synchronized with the previous one. So for the tree one, it of course are the servers that are synchronized with the stratum in layer 2, and so on. And then user computers are synchronizing with these stratums, or with these NTP servers that are synchronized with this, and this is with this, and this is with this, and this is with this. Anyway, that's how we are basically we are having accurate time at the moment. Okay, this is what happening in the network at the moment. As Sergey checked Christian algorithms were belong to 31 years ago. Those times internet was not as reliable as now, not as fast as now, so there was a lot more issues by then. But now the communication is very much reliable, okay, and we can keep our basically computers synchronized using this structure. So messages between FTP client and servers are exchanged in pairs, request and response. They use Christian's algorithms. So for ith message exchange with a particular server, we calculate the clock offset or theta from client servers. And also we calculate the round trip times between client and server. So over last 8 exchange with server K, the client computes its depression. So in order to do that, you exchange 8 message with the time server that you are connected with as like a local computers or normal computer. You are connected with Stratum's layer 3. So basically, you exchange 8 message and then you calculate the dispersion, and then based on that, you can calculate the local time. I mean, estimate the clock offset that you have in your local system. So this is the question that I guess Sergey was asking, how do we change the time? Okay, let's say I understand that my local time, not me, my computer understand the local time is basically have offset. How we do this skewing? Skewing means like gradually changing. How we gradually change the time? As I mentioned, we cannot just change the time because we don't want to run backward. Let's say I find my clock, internal clock is running faster than actual clock. So I cannot just go backward in the time because that can cause a lot of issues locally for my local procedures that are running constantly, right? So for that reason, for example, recall the first example I mentioned about the running compiler. So we cannot just do that, okay, simply change the clock. Instead, what we do, we change the update rate for the clock. So we change the time in more gradual fashion. So, and we prevent inconsistent local timestamps. So we don't want to have inconsistent local timestamp. That's why we need a slow skewing. So we change, for example, in order to do that, we change the virtual frequency of the software clock to make the clock go faster or slower until the requested correction is achieved. For example, in the example that I did, it is a very simple one that we find out that we need to recover 0.2 seconds. So what we can do, we can just increase the virtual frequency for the software clock in order to gradually achieving or recovering from that 0.2 second clock offset. And for example, standard Linux adjusts the time with the rate of 0.5 millisecond per second. That's the basically microsecond, sorry, a millisecond per second. Okay, that's how we're changing the local clock if we find any clock offset. Any questions so far? Is that clear? I mean, understood completely? Juan, how do you feel? Juan Pablo. All good?
I'm feeling
lost.
Yeah, lost and overwhelmed, but I don't want to like slow down the rhythm of the crypt, so I'll.
No, it's fine. You can always ask. Anyway, the whole idea here so far. Okay, I mean, let me take you this one. The takeaway point. Okay, I don't expect you to know exactly that 9,100,000 something second. Okay, the frequency of the atomic clock. Those are not the knowledge that you need to remember. These are the basically takeaway points so far. We know clocks on different systems will always behave differently. Okay, So there is a disagreement between machines can result on undesirable behavior. If we have machines that are not synchronized, that can cause problem. So NTP clock synchronization, we talk about this. We rely on timestamp to estimate network delays. So we have up to hundreds of microsecond to millisecond accuracy using like NTP. But the thing is, clocks never exactly synchronize. And when we're talking about time, it's not that you can get two systems exactly synchronized on a time. There would be always a clock drift, but in like a, how to say, acceptable level. So those clocks that we just talked so far, those solutions, the good point is they are often inadequate for distributed systems. Okay. So far we talk about, okay, we have clock drift, how we can solve that using like GPS system, using NTP, using Christian's algorithm, combination of those in an NTP, but yet they are sometimes or often inadequate for distributed systems. So in distributed system, we often need to reason about the order of the events. And when we're talking about distributed system, the order of the events is very, very important. Because we want to know what happened first, then what happened, then what happened. Those order of the events is very important when we're talking about distributed system. So we might need precision on the order of nanosecond if you want to achieve that precision. And relying on only the wall clock time, we might be needing to have a clock by nanoseconds of accuracy, which is not easy to achieve. So for that reason, what we talk about logical time or Lamport clocks. If you remember, I mentioned this guy named first class. So before I continue, let's have 7-8 minutes break, okay? So we can come back by 7:40 sharp. I hope your clock is synchronized with mine, okay? When I see 7:32, so we come back by 7:40, okay?
Okay.
Okay.
It's all right. So I said all those things that we were talking so far might not be so sufficient talking about distributed system. And in distributed system, order of the events is very important. So let's talk about logical clock or logical time or Lamport's clock. So before that, let's think about this scenario. You have a New York-based bank that wants to make its transaction ledger database resilient to whole site failure. This is one example that I don't remember exactly who was talking. I think Paul was talking about. You can replicate your database because you want it. You don't want to like your whole site fail if something happens, let's say a natural disaster. So you replicate your database. So let's say these banks want to replicate the database. So it has one branch in New York, another one in San Francisco. So we have a replicate of the database in San Francisco and the bank is in New York, okay? So a client can send a query to the nearest copy and client also can send update to the both copies because if this is my account balance is $100, okay, this $100 should be basically synchronized where it should be equal in both databases. I cannot have 200 here and 1,000 here. If it's my bank balance, it should be exactly the same. So imagine this scenario. And let's say I'm going to deposit $100 to my account, okay? And the bank is going to pay me 1% interest, just on a simple scenario. So I'm here close to the bay here in San Francisco. I deposit, because I'm closer to here, I send a query to the closest copy. Okay, my query goes to the closest copy. So I update this database. Now here I have $100 1,100, and here I had 1,000. And when the bank wants to pay me interest, it checked my account and it sees 1,000, it paid me like 1% interest, and it increased my balance to 100,010, and then then it received my deposit of 100 information later. I mean, I couldn't be fast enough like the animation to tell everything. But basically, if these two events are happening, let's say at the same time, or in two different locations. So here I deposit 100, I update this database first. This is paying 1% interest to this database first, okay? So this would be causing a problem or a mismatched replica. Is it clear? So we have here the problem, which is inconsistent replica. So updates should have been performed in the same order at each copy. It shouldn't be performing in different order. The order of the events is very important, right? That's why in this request for comments 677, which was talking about the maintenance of the duplicate database, blah, 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 not whatever. Here it says the distributed nature of the system dictate that this property can never be 0. Which property? The strange behavior because of the basically the clock difference. Okay, this doesn't matter. So here comes this bright guy, Lamport, Leslie Lamport. He had this landmark paper in 1978. He came up with this idea that why we need to rely so much on the wall time clock, why we don't go with a logical clock. And what does it mean? Basically, the basic idea is we only care about the event themselves, not the time. I want to know the deposit happened before paying the interest. It doesn't matter in which time they happen, okay? It's important for me to know this happened before this. So the order of events is important, or basically the events themselves are important. So the idea is disregard the precise clock time. Instead, capture just happened before relationship between a pair of events. So you have a pair of events, ignore like that nanosecond accuracy and just try to know this event happened before this event. Try to record that, okay? That's the idea. So let's define what does it mean happen before, okay? I'm going to show it with this arrow, okay? Like A happened before B, okay? So if I put this, it means A happened before B. And consider this scenario, we have 3 processes, different computer. So when events happen in one process, it's very easy to calculate or to know order of events, right? If I'm doing just something in my local computer, of course, it's very easy to know the order of events because I have a local clock and it's recording the order of the events as it goes. So there is no issue here in these 2 events, A and B, when it's happening in one processor. So here we can say if they happen like this, okay, if same process and A occurs before B, then A happens before B. Okay. So we can also observe ordering when processes are communicated. For example, when in this example, if process B communicate to process C, then, or basically if the C is a message recipient of B, then B happens before C. In 2 different processes or 2 different locations. So we can observe the ordering transitively as well. So what it means, if A happened before B, B happened before C, it means A happened before C. So far, so good. Okay, right? Clear. So this is the physical time. It's like time is growing. We have theory processor. But the issue is here, what about this event T here, happening here in the process 3? We cannot have that happen before relationship for all the events. For example, it's not like A happened before D, or B happened before D, or C happened before D, because there is no communication between these events. So we can say A is concurrent with D in this example. So far what we are talking about happened before relationship. If a process happened before another process in one, if this event happened before this in one process, so clear, A happened before B, because this is the physical time in this processor, you can record that. When it's in two different processes, if C is recipient of the B, it means B happened before C. If there is another event that has no connection with other events, we cannot say anything. We say it like A is concurrent with D, or A is concurrent with D, or B is concurrent with D. We don't know which one happened before which. So is it clear so far? Okay, so the objective of Lamport clock is we seek a clock time for every event, let's say A. So if I put like this, it means clock time for event A. So what we do, we tag events with clock times. We use clock times to make distributed system correct. Okay, we're not purely going to rely on the timing, but of course we're going to use that. So this is the condition, clock condition. If A happened before B, then clock A should be smaller than clock B. It's clear? If A happened before B, this is for sure is the case. CA, or clock time for event A, is smaller than clock time for event B. So how about the reverse of this condition?
It should be the same, right? Because
if
otherwise
CA
it's a
is
contradiction.
smaller than CB, can I conclude A happened before B?
Yes, otherwise it's a contradiction, right? You can guess.
Yeah, true. I mean, from the reverse, I cannot conclude this. If CA is smaller than CB, I cannot conclude A happened before B. But I can conclude if A happened before B, then CA is smaller than CB, not the other way around. So consider, remember this example. Each process, P index I, maintains a local clock, CI. So basically, P1, P2, P3, we have these three processors. So this is C1 happening starting from 0, C2 0, C3 0. Okay. So when we execute here the first event, okay, so we set event time like this, CA to CI. So now CA is 1. Here CB, okay, is 2 for the event B. So this is send the local clock in the message that we are communicating between these two events. We send the local clock. So basically, I'm going to include this CM2 in my message and send it to the process 2 to the event C in process 2. So before this message is received, this is the case here. C2 is still 0. So this is going to arrive here, then the timing for the process 2 for the event C will be 3. That's it. It's clear so far? It's more like basically notation so far, okay? I'm talking about how we're going to see these things. But any questions so far? So far, we are recording basically the timing, the event, and the clock time for each processor. So if another event is going to happen here, let's say D, then that's going to be full, right? the clock time here going to be 4. And if this event is going to communicate with this event, then this is going to be 5, right? So let's look at this example. We have process 1, process 2, process 3. So you tell me which one of these is correct. Is it A happening before B?
Yes.
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 B happened before F?
Yes.
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 A happened before F?
Yes.
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 A happened before H?
No.
We don't know.
We don't know.
We don't know.
Concur.
Okay, F and J?
Yes.
Yes.
F
Yes.
and J?
Yes.
Okay. C and F?
Yeah. We don't know.
We don't know.
No.
We don't
Okay.
know.
H and J? This is
Yes.
H.
Yes.
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 And H and
Yes.
C. H here is C here.
I would say yes.
No, we don't know.
We don't know.
We don't know.
We
Okay.
don't know.
But
Let's go.
if we know that B happened before C,
Okay.
and we know that E happened before F, then I'm assuming that H did happen before C.
That's good observation. Let's see. Let's see how it
Okay.
goes. So let's, oh, it's gone. Okay. I'm going to back to this, refer to this. Okay. So let's put that timing. Okay. So we can see this is the first event here. First event here. I'm putting basically the clock time for them. So this is the I mean, based on the condition, what we talked about, this communicated with this. So this should be 2. Where is my... So this is 2 because happened before A. This is 3 because happening before E. This is 2 because happening before H. I mean, after. Okay, no, sorry. After this. This is happening after D. Happening after F, D, E, and J. Right? So this is correct. This is correct. This is.
I have a question.
Okay.
In process 3, we have that H has a value of 1 and E has a value of 2, and also I has a value of 2.
Mm-hmm.
But in process 2, oh no, my mistake. No, my mistake.
Because
sorry.
E has 2, because
Yeah.
E get the maximum always.
Yes.
Maybe, yeah, because it's, you remember, let me show you the equation. This one. This one.
Yeah.
You get the max.
Yes.
So this is the things. So let me show you this, and we can discuss this. So you said this is 1 happened before 2, okay? 2, B and F, true. A and F, true. Then A and H, we don't know. F and J, true, right? F and J. C and F, we don't know. C and F. H and J, H and J. Of course, when they are happening in one processor, it's very easy, right? You can say for sure. And H and C, that was when we were, I mean, Juan was having doubt. Of course, you remember what we were saying? If A happened before B, then for sure CA is smaller than CB, but the other way around is not correct. Of course, HC here this one, CH, the time for H is smaller than time for C, but we cannot conclude from this that H happened before C.
Why? Because
It's that's a tricky question. Why? Because that's how we're setting the rules. Okay. Because when A happened before B, for sure I know this the clock time of A should be smaller than B. Okay, but just based on the clock, I cannot say this happened before that because they can be totally independent events that they have nothing to do with each other. They're happening just in different time, but they have nothing to, basically they are concurrent events. They're not having this happen before relationship with each other.
okay.
Okay. So it will be more clear when we go along. So don't worry about it. We're going to talk about this logical timing a lot. So we can use this Lamport timestamps to order all the events, okay? So we can break ties by appending the process numbers at each event. For example, this type of issues that we have here, the ties, okay? If like what I want to do here, I want to order all these events. I have them, but I cannot, at this moment, I cannot order them, right? I cannot put them in order from first event to the last event for all three processors. What I want to do, I want to order all events. So we can do that by appending the process number to each event. So process PI timestamp event E will be like this, CIEI. Basically what I'm trying to do is don't get confused. I'm going to append this process I to this clock also. I'm going to say like this is 1.1, for example. So then this wouldn't happen. I get here 1.1, 1.3, so I order 1.1 before 1.3. I mean, that is as simple as that. So when we have this, CA is smaller than CB. If this is smaller than this, it means CA is smaller than CB, or they are equal, but the processor index for I is smaller than J. Exactly what I said here. If I put here like this, like let's say I say this one as 1.1, okay, and this one 1.3 because it happened in process 3, then I can say this is smaller than this, right? Because either the clock is smaller or the ID or the index of the process. I mean, this is what is there. I mean, don't get confused with the, sometimes the notation get confusing, so don't just get confused with them. So now for any two events, A and B, we can have this one. Either CA is smaller than CB or CB is smaller than CA. Clear? So we're not gonna face this problem anymore. To have them equal. So we can order all the events. So the whole idea here is to order the events, okay? So how we can order these events? You tell me.
By using a timestamp.
Yeah, you tell me the order of the events that happen.
Ah, okay.
Of course, it start with A.
B.
Then B.
D.
D.
F.
F.
H.
H.
And then I don't know if C or E.
I think it's C.
Which one? So after H is C?
I think so because it's going to be
Okay.
C1
And then?
or 3-1.
And then E.
E.
Then I.
And then
I.
G.
Okay, let's see. Let's see how accurate is that. So CA1, basically event clock for event A in the process A, right? In the processor 1. This is referred to this, okay? So that is 1, even B is 2, here even D is 3, even F is 4 versus 3, this is 5, this is 6, this is 7. So far, so good. What would be for this? C, let me see, CC 0.1 equal to
3.
3.
3. So then this would be equal to this.
Uh-huh.
Which one should go first?
C.
C?
C.
Okay. Yeah, that was what you said. So this was wrong right from here.
Okay.
So let me remove all.
And only because it happened in the processing line of
Yeah.
1. Okay.
Yeah, that's a condition we put. Because we don't want to have 2 events having the same clock equal.
Okay.
But if they have equal, then we cannot order them.
Uh-huh.
So far, what the whole idea is, we want to know which events happening before which event happening before which event. We want to know all the order of the events, right? Because we are saying in distributed system, order of the events is important. So, so if I put all of them, the timing like this, then you can see these two are equal, right? These two are equal. I mean, by equal, I mean this part, this value is equal. These two values. So now if you say the order, it would be like this, right? A, B, C, C because the index is smaller than this. This is index 1, this is index 2. That's just the agreement that we put, right? You want to order it this way. So A, B, C, D, E, F, H, I, G, right? Is it clear?
It is.
Perfect. So let me. So the whole idea so far is like totally ordering multicast packets. The goal is all site applies update in the same Lamport clock order. Like, so we don't want to have that issue that we saw in a depositing and paying interest. So clients send updates to one replica, site J. The replica assign its Lamport timestamp as this. Okay, so now we are ignoring the clock. We are going with the Lamport timestamp. And we are trying to order all the events, all the updates. So the key idea is placing events into a sorted local queue. So we can sort them by increasing Lamport timestamps. You remember this is I'm talking about that example that we mentioned about the banking. So there the issue was events was happening not in the same order in 2 different replica. So the whole idea here is we want events to happen in the same order in both replica. In the New York and San Francisco, the events should happen with the same order. That's why we put them in a local queue, and how we order them based on the increasing Lamport timestamp. So if this is 1.1, this is 1.2. It's clear? So we can have two different ways. I mean, not 2 different ways. It's like, this is what I'm trying to say now is a almost correct version, not exactly correct. Then I say you exactly correct way. So what we can do, we can, on receiving an update from clients, we broadcast to others, including ourselves. So I'm in San Francisco replica. I'm the San Francisco replica. I received this $100 deposit. I received this request, okay, update from the client. I need to now broadcast this message to all the replicas. Let's say to the other one in New York, and also to myself. okay? On receiving an update from replica, add it to your local queue. So when the New York receiving this message from San Francisco, it's going to add that value, that request in a queue. Then what you do, you broadcast an acknowledged. I mean, let me do something. Sorry about this. I don't want to say that almost correct. I'm going to say to you that it's just the correct solution. Okay. On receiving or processing an update, add it to your local queue. Okay. If you receive the update, add it to your local queue. Then you broadcast an acknowledgement message to every replica, including yourself, only from head of the queue. Is it clear? So I'm going to show you with the example. So when you receive the acknowledgement, marks corresponding update acknowledged in your queue. So you remove and process updates. You remove and processes updates. Everyone has acknowledged from head of the queue. It's getting confusing. Let's go here. You remember this one? Depositing, paying the interest. This is the New York replica. This is the San Francisco replica. So this is happening locally in my process 1. So its first event is 1.1. This is happening in this replica. Okay, it's an event 1 in processor 2. Is it clear? So I get this update from the customers. What I'm supposed to do, I'm supposed to broadcast this message to other replicas. So I, in San Francisco, broadcast this message to the New York, and the New York going to broadcast this paying interest to San Francisco replica. So I'm going to send this, and New York going to send this. So when I receive this percentage here, I'm going to add that into my queue, right? This is the queue of the events, right? This is my local queue. I receive this request. I add this to my queue. And also this request will be arrived to this New York replica. So when New York replica receive this 1.1, it's going to put that in the head of the queue. Mm-hmm. Because it's putting that in the head of queue, because it has a smaller index than this, it put that in the head of queue, and when it's in the head of queue, it sends me the acknowledgement. Once I receive the acknowledgement from all the replica, in this example, we have just 2 replica. When I receive the acknowledgement from all the replica, I start processing from the head of the queue. Okay? So that will be processed, and this will be processed.
Okay.
So now both replica are like, if you remember that example, they are now 1,100. The balance of account is 1,100. That event happened in both replica. And then this is now in the head of my queue, right? So I send the acknowledgement to myself and to the other replica. So when I send the acknowledgement, of course, I acknowledge, I start processing and removing from my head of the queue. And upon receipt of that acknowledge, this process also going to process it from the head of the queue. Was it clear?
I have one question.
Sure.
How do you know which is the primary process, which is the one P1 and P2, depending on the distance to the user?
I didn't catch your question.
In this case, San Francisco is P1. That's why it is in the head of the queue. And New York is P2. But how do you decide which one is P1 and which one is P2?
That can be just an agreement. I mean, let's say this is the primary replica, this is the secondary replica, this is the tertiary replica. Just give, the whole idea is giving like ID to that process.
Okay.
I mean, I mean, don't get confused here. I'm talking about like P1. Okay, it's process 1. Okay, In reality, let's say if we use this in reality, that ID might be totally something else. That ID might be just the IP, for example. Okay, who has the lower IP? Because I mean, what I'm talking about here is more like, how can I say that? More than conceptual. Okay, so far. So you imagine however you like to get agreement on this. Which one is the smaller like process, or which one is the which one is like, let's say the primary one, which one is the secondary one.
And can it be like, do you have more examples of how they agree in the real life? Like it can be based on time, it can be based on IP addresses.
No. Here, okay. I think I'm being more confusing. Let's say just this is the primary one. This is the primary. It has the ID, lower ID, P1. Okay, it has ID 1. We just said, I mean, I'm setting up, right? It's my bank. I'm owning this bank. And I said this replica ID is 1, this replica ID is 2.
Okay.
I mean, just let's simplify it. Okay? It's more like conceptual. So, okay, what I skipped, I mean, let me show you. I skipped one. I thought time is different. This is what I was trying to tell you before earlier, like the almost correct version. I just skipped. I didn't say, because what you can think of here is like you say, okay, I have these events, okay, then I transfer them to the other one, then I put them in my queue, okay. I put this in the queue, I put the other events in the queue, but if you don't start processing from the head of the queue, you're not going to have perfect synchronization. So that's why I was putting here almost correct, to later to tell you why you need to process from the head of the queue, okay? So I just skipped that because it's not important. The important is the correct way. This is the correct way. So you do this, you order them. As long as you get, you put that in the head of queue, you start acknowledging. As long as you acknowledge the events, you start processing it from the head of the queue. So you don't start here, you don't start processing with this, because this is not the event in the head of the queue. Even if it's acknowledged, doesn't matter. You start processing from the head of the queue. That's the whole idea of the queue. So, okay. Any questions?
Yeah, I have one.
Go ahead.
Are there any mechanisms to handle errors? For example, if acknowledge is missing, or the request takes too long, how the replica knows that, or the system has to know how to handle those errors?
Perfect questions, Saul. You just jumped 1 week in advance. So basically, that's what I'm going to explain here.
Okay.
Are we done? Okay, that's a question actually Saul asking. So does totally ordered multicast, what we just talked today, solve the problem of multi-site replication in general? Not by a long shot. Okay, we just started talking about it. Because we assumed no node failure, none of the replica is failing, no message loss, as Paul said. What if the message loss? What if the message get corrupted? We didn't talk about any of this, okay? So we're not done. We just started talking about it. I'm going to cover those in a few of future lectures, because talking about this totally ordered multicast and multi-site replication, which is very important in distributed system, it's really complicated things. No, forget it. It's not complicated, but it's not this simple, because Because again, we were talking about the internet the first week, network in general, it's not reliable. I mean, we feel it is reliable because of all these things that they already consider and they know how to deal with this type of issues. And me and you as users, we never feel that there were a message loss, there were a replica failure, there were some message corrupted. We never feel it because they already solved all these issues. And we are going to see in the future how we can overcome those issues, like a message corrupted message, and failure message. Maybe in this example, maybe this replica is failed. Here I'm just simplifying, just talking about 2 replica. But in reality, it's way more replica than just 2 replica. And what happens if 1 replica totally dies for sometimes, sometimes let's say 5 minutes, and then join the network again? How we can keep that updated? I mean, all those issues that we're going to talk in the future sessions. Any questions about it? No? So if there is no further questions, so I'm done basically by my talk. So, and another thing is important is all-to-all communication does not scale. Okay, I'm talking here about 2 replica. What if I have like, I don't know, 10 replica, different state in the United States, not even talking about different continents. So in this example, I'm talking about all-to-all communication, right? Both replicas are talking to each other. What if we have 10 replica? All these 10 replica are going to talk to each other, communicate with each other. Then if that's so, then it's not scalable, right? And also wait for the message rates. And another thing, as I said, if the message is lost, is the replica going to wait forever to receive the acknowledgement? So those are the things we're going to talk in the future classes to see how we deal with those problems. If there is no further question, let's have like a 5 minutes break. Okay. Then we continue with 1 more slide from me and student presentation talking about MapReduce. So let's come back 8:30 sharp.
Okay.
Okay. Thank you guys. Okay. Again, I'm here if there is questions.
Hi.
Sure, go ahead.
Thank you, Mati. Can I ask you if you can explain me a little bit more the other algorithm? It was not Christians, it was Berkeley's algorithm, just to...
Sure, let me...
Thank you.
Find my pointer. Go to Berkeley. Okay. Here in the Berkeley algorithms, we say we want to have a distributed synchronization, not relying on one time server. Okay. You remember in the previous one, we were talking about synchronizing with a time server.
Okay.
So in Berkeley, we are saying we don't want to have a time server. We want to have a distributed synchronization between a set of systems, a set of computers.
Okay.
And how that can happen, let's say in this example, we have 3, okay? So one of the computers is going to take the master role, okay? And this master computer are going to start pulling other machines' time. So this is the master, this one in this particular case. This is the local clock. I see this in my clock as a master. So I'm going to ask other computer what are you seeing in your clock?
Mm-hmm.
So this tells me I send them my clock, okay?
Mm-hmm.
I send them, okay, I'm 3, I send them, I'm seeing 3, I'm seeing 3, I'm seeing 3 to myself. So this is going to reply to me that my clock is like has 10 minutes behind, okay,
Mm-hmm.
minus 10. It's going to reply my message, I'm plus 25, like more ahead of you.
Mm-hmm.
So I receive all these values. 0 is from myself because my clock is 3. I send this 3 to myself also, so I get 0. And I have minus 10, I have 25 here, plus 25. If I sum them, I'm going to get plus 15, right?
Uh-huh.
So I have 3 computers, right? So I average this and I get plus 5, right?
Okay.
So what does it mean? All the computers here, now we want to change our time to with the plus 5 value. So I'm going to send this plus 5 value, or I'm going to basically tell all the clocks let's say, how much they need to change their clock.
Okay.
So I send myself 5 because I'm 3 already, right?
Uh-huh.
So I need only 5 extra. This was minus 10. In order to have plus 5, I send this plus 15.
Okay.
This one was plus 25. So I send it minus 20.
Okay.
So then they're gonna you're going to all have the same clock.
Okay. And it says that using Christian's algorithm. So
Yes.
to send the master uses the Christian's algorithm to send the clock and okay.
Yes.
Thank you.
So the same process that's happening here will happen there too. This process.
Mm-hmm.
For all those communication with other clocks, we use this Christian's algorithm.
Okay, so that means the master knows the clock, the time of the 250 clock, dividing the sigma by 2, no?
Mm-hmm. Yeah.
Okay.
So yeah, I mean, imagine all those communication, like I'm sending, what I'm receiving. Okay, all those calculation that we did in the Christian's algorithms.
Thank you. Thank you.
Okay, guys, if you're here, please turn on camera. Let's conclude today's class. So what are the takeaway points? I was recording on the break. Second. So the takeaway points from the Lamport clock is we can use that in order to totally order events in distributed systems. Okay. We didn't solve all the issues, but still that's pretty useful application. We saw an application of Lamport clocks for totally ordered multicast using that banking example. If you remember, while by construction A happened before B implies CA or clock A is smaller than clock B, the converse is not necessarily true. So if clock A is smaller than clock B does not imply A happened before B. You cannot conclude from this, you cannot conclude this. From this, you can conclude this, but the other way around, it's not possible. It's not basically applicable because it can be like A and B are concurrent. There is no relationship between them. We can't use Lamport clock timestamp to infer causal relationship between events. Causality is another very important topic in distributed system. What is causing what? Okay, this event causing the other events. we cannot use Lamport clocks in order to know that. We can use them for ordering the events, but we cannot use them for causal relationship. So we need something else to have this causal relationship between two different events. Is it clear?
So then what do you use for causal relationships?
I'm going to talk about it. Like, I guess maybe 3 just classes, we're going to talk about causality. As I mentioned, this will be used. We're going to consider this for a lot of more things, but not just this. As I mentioned, this is good enough for ordering all the events, but not yet, as I mentioned, not yet considering all the issues that can happen, a replica failure, a message loss, message corruptions. So, we just started talking about it. So that's it from my talk. And let's continue with talk about MapReduce by, who was that? Roberto. And Robert, are you ready?
Yeah.
You were teaming up with, I forgot.
Javier.
Okay, so you both here?
I think so, yeah.
Okay. So I stopped sharing. Okay, before they start talking, let me tell you what I expect you to do. Okay, the students, I expect you to listen. Okay. And I expect you to understand, because later I'm going to basically ask you what you understood from their presentation. And also that helps them to gain grades. Okay. I remember last year, there was a big complaint about it, that I don't like this, why my grades should be based on other student opinion. But I will stick with that, because I believe that's a good practice, because I want you also to pay attention, not just to what I'm telling. This MapReduce, I'm not going to talk about at all. So if you want to know about MapReduce, this is the time, and this is the only talk we're going to have on it. So
how about if we have questions?
Yeah, it's totally the same rules applies with them. Just stop them, ask questions. Yeah, of course, I mentioned, if you remember, if you see that, maybe I'm going to show you the rubric of the presentation. I think they already have the presenting people, but it's important. I consider big time of it. It's okay, go ahead. You can share. I show that later.
Oh, okay. Yeah, I just have a question. If they would stop us with questions or doubts, should we, I have a timer here because we need to be like 20-30 minutes duration of the talk, so I rather have the questions at the very end.
Okay.
And maybe as an advice, maybe you can just write them down and then come to questions at the end of the presentation. Okay. So Javier, can you start?
I can't hear you.
Can you hear me now?
Yep.
Yep. Okay. So my name is Javier. My partner is Roberto, and we're going to present to you about MapReduce. So MapReduce basically is a programming model for processing and generating large data sets. And the way it basically works is that users specify a map function that processes information from data you already have and generates intermediate values. And then a reduce function merges the intermediate values, so the data set becomes smaller and easier to read. So it is easy to use. even for programmers with very little experience with parallel and distributed systems, because programs are automatically parallelized, and they are executed automatically on a large cluster of machines. And that cluster can be from really small numbers of machines to thousands of computers working at the same time. And the runtime systems already handles the partitioning of the input data, the scheduling the execution across a set of machines. It handles machine failures and all the inter-machine communication. And Google uses MapReduce on thousands of jobs every single day. So it is a very handy tool. So the way it started is that Google uses a lot of special purpose computations that they have to process a very large amount of data. So like with web request logs, crawled documents, etc. And the computing, well, the computations used are really conceptually straightforward, but the input data is really, really large. So it's not very efficient to use it all in one single computer. So they have to be distributed across many machines to finish in a reasonable time frame. And all that parallelizing, data distribution, failure handling, inter-system communication can be very complex. So Google designed MapReduce as a program to hide the complexities. And it does all of the above automatically. So I don't know if, Roberto, you can talk about the programming model.
Yeah, on how MapReduce works. Actually, the idea is to have basically just three phases. The name of the MapReduce is composed by two of the main functionalities used in functional programming, which is map and reduce, and those are heavily used functions. And the idea is to provide a really large data set or source file that needs to be presented in a way of a map in order of key and value. And this is the input map. And the idea for the mapping process is to leverage an intermediate maps, which is a key, which is noted here on the slide as key 2 v2. And these intermediate maps will be sorted in a way that they will be split into different intermediate or temporary files that will be spread across the network. And depending on these intermediate maps, the shuffling will happen, which is we will take all the tasks to different nodes, and those nodes will have probably the same task or the same reduce task that they will perform. Now the reduce task is about reducing all the map key values to just one single value for each key. So that will happen on the reduce function. So the idea is to have as a final result, as in here on the slide, I just found out this image on the internet, which is showing the example with just one output, which is bear, car, deer, right, river, which is the counting of words in just one file. But the idea is actually to have different files as an output, as it will be an input for a second MapReduce cycle, or it also be part of the input of a different distributed system that will handle those files. So the overall idea of this diagram is that we will be counting words on a very large input. In this case, we are providing the deer, bear, river, car, river, deer, car, bear. And the idea is for the splitting functionality, which is the map part of the MapReduce process, to come up with these input key values, which is key 1 would be the first line of the text file. Key 2 will be the second line, and key 3 will be the third line. Then those will be sent out to the map workers. Those map workers are actually given by the programmer or the user of the MapReduce. And then in this case, we have 3 map workers. What they are going to do is to start counting the words, to first split the words by space, and then those would be given as a key, and then they will start counting the words. Like on the first map worker, we have deer, bear, and river as 1. The same happens on the other workers. And the idea of the shuffling phase is that we will put everything for the reduced worker as a list of intermediate key, which in this case would be the words, bear, car, deer, river, and then we will put all the counts for the that are the output for the map workers. Then we enter to the reduce phase, which is we will count or sum all the occurrences for this word in the text file, and then this is the output. Again, in this case, it just shows an output, but I decided to put here that you will have, like, for example, a file name, bear, car, deer, and the content would be the coincidences of that word. Then here are some of the examples that we will explain.
Yeah, so you can use MapReduce for many different types of programs. So one is distributed grep. So the map function emits a line if it matches a supplied pattern, and the reduce function is an identity function that copies all the intermediate data that the map function generated into to an output. So then the count of URL access frequency, the map processes all the logs of web page requests and outputs. So the counts of each web page, of each URL, so it counts them. And then the reduce adds together all the values for the same URL, so you can see which web page request was the most or the least requested. The reverse web link graph, so the map outputs target and source pairs, and the reduce concatenates a list of all the source URLs and emits a target with a list of all the sources. The term vector per host, the term vector you have a term vector that summarizes the most important words occurring in a document or a set of documents as a list, and the map emits the host name of the document and the term vector of the words occurring for each document. And the reduce vector then adds all the term vectors together and emits a final host name and term vector pair. Then we have you can use it also for inverted indexes, and the map function parses each document and emits like word and document ID pairs, and the reduce function accepts all the pairs, sorts the document IDs, and emits a word and a list document ID pair. And all of the output pairs form an inverted index. And then you can do this sort of the same thing for distributed sorting, but the map extracts a key from each record, and reduce just emits all the pairs that the map extracted already for distribution. So one thing that my partner didn't explain is that you have to the MapReduce library partitions all of map functions or pieces into small chunks like 16 to 64 megabytes per piece, and starts many copies of the program on a cluster of machines. And the one copy is the master copy. So all of the rest of the copies are assigned works by the master, and the master is like the most important part of the MapReduce function. What's next?
Okay, the MapReduce characteristics. First, we have the input-output. So the input it could be defined by the user. It could be like several set of files, or just a single large file, or even it could be different records coming from a database. The output is usually a different type of files with the already reduced values on it. And again, it's usually a different set of values that it could be an input for another MapReduce process, or it could be an input for a different distributed system that is expecting the same kind of input as the output that it's producing. But again, you can just produce a single file, or you can even again post against to a database. The master worker and the master data structures. This is the part that we already talked about. There is a master computer, which is the one that is scheduling all the works, and it's dividing or splitting all the that provide the initial map key values, the input ones, and this master keeps a master data structures, which is a record or a data structure that actually it's pointing to a different nodes on the cluster, and those nodes will have certain works scheduled, and they will mark it as new job, or work in progress job, or in progress, or as a finished task. Now the idea is to have this in a data structure, because we will need to just in case that one of the nodes fails, this data structure is actually copied, and then this would represent a state of the machine, so it can be brought back, in function to the cluster. Then we have this is part of the fault tolerance. There is also another way to tolerate the faults on the cluster, which is if some of the nodes fails, the master keeps a record for the non completed tasks, and then this will be rescheduled with the remaining nodes that are still on the cluster. There is another engineering here that once a node fails, all the tasks that were sent to this node, even if they are already done, they are marked as invalid, as there could be a possibly loss of information. So all of these tasks will be set as invalid, and they will be reprocessed in different nodes. Now, let me just jump to the backup task, which it's kind of related. The backup tasks are like, okay, I will schedule the same task into different nodes, and the idea is to have, if you have a faulty node, or a node that is taking too much time to return with the results, then the other node is completing the task rapidly, or quicker than the other node, then this one will slow down the system, and then this will be reflected on the performance of the MapReduce entire functionality. And you can see that on the performance rate that we will show later on another slide. We also have the task granularity, which is you can as a user, you can set how many map workers do you want and how many reduce workers do you want. So the task will be split up into those different map workers and reduce workers. The idea is for you to actually use the entire cluster or just a portion of the cluster. But the idea is just to define how many map workers do you want or how many reduce workers do you want. Sorry, I skipped the locality one. The locality is just it's a simple one, which is just the network one, which should be just locally arranged. And there is also another thing that it's called the global files, Google file system. Again, this MapReduce module is proposed by Google people, so they are using the Google file system, and they are proposing that because there are a lot of files in exchange. One of the things that I probably didn't mention on the master data structures is that also there are some pointers to the files. So the files are kept locally on the storage for each of the nodes, but eventually they will move to they will be used for the different reduce functions. Again, the map combine and reduce function. The map and the reduce function, it's provided by the user or the programmer. And let me just stop sharing just a little bit and then start sharing again on a basic sample that I have. So this is, let me just go to the mapper. So this is a Java code that just to show how easy it's to implement the MapReduce module. And I already have the cluster installed in my computer, but unfortunately I did some tests at the very beginning of the class and it's not working with Zoom and video and sharing screen. So I'm just going to show the code, but if you would like to see it working, I'll try to do something like a video or something and I upload it on the class. It's based on Canvas or something. But the idea is just to have this code count mapper. I'm using already a Hadoop, Apache Hadoop implementation of the MapReduce. So the idea is just for you to implement the mapper class, and the idea for you is to have a map method. And for this particular example, I'm going to count words, and I'm assuming that my input is a text file, and I will split the text file through through words or in between words, and divided by space or split by space. And then what I'm going to do is just to count each word as a one or with a value of 1. The combine function, it's tricky because it could be the same as the reduce function. The idea is just to help do the sorting of the reduce works or tasks that you will distribute across all the nodes. The reduce method is just simple. I will get a key with all the which is the word, and then I will have all the values, which are the counts or the number of counts that they were found through the map workers. And then what I'm going to do is just to keep adding those values, and then I will output a file with the name of the key and then the value of the counting of the words. So that's basically it. And then, well, I have my application, which is just an implementation of the job. And a very special thing here is the configuration object, which you can, through this object, I just use the default parameters, but the actual configuration object, you will be able to set how many map workers do you want, how many reduce workers do you want, and the file size of that you want to split the first key value mappers. And I think that's it for the code. Let me just go back to the presentation. Sorry, I can find the presentation. Here it is. So that's the map combine and reduce functions. Then the status information and counters is just the map reduce module or model provide a UI where you can actually monitor how many workers do you have, how many nodes are you using, the counters of how many tasks that particular node has been processed and things like that. And of course, we have a value or a parameter that you can actually set on the configuration object on how many skipping back records you can have. Like, for example, for statistical purposes, you would like to process all of the values, but if there are some certain values that can be processed because of computing reasons or faults, you can just skip those and take certain percentage of the data evaluated, and that would be a really good result still for the map reduce. So as you can see on the code, it's really simple. You just implement 2 or 3 lines, and then you let the map reduce to do everything, and that actually create the cluster, create nodes, distribute the works, and if you can think it as silly as the text file would be like a petabyte, large. If you do it like in a single thread or in a single processor or in a single node, that would take like ages to process. So the idea of the map reduce is for you to distribute that file across the different computers and nodes, and that it's being done for the map reduce entirely. So I didn't know what happened behind the scenes on the map reduce library. Let's continue with the performance.
Yeah, this is a test run by Google. They used the MapReduce for a sorting computation, and this sorted 10 to the 10th power 100 byte records, so like about 1 terabyte of information. And the input was split into 64 megabyte pieces. So there was 15,000 map tasks, or that had to be distributed between the workers, and the output was placed into 4,000 files. So there were 4,000 reduce functions. So the normal execution is the first column, where first the input is distributed among all the workers for the map tasks, and as you can see, it runs at about what is it, like 10,000 megabytes per second, or 12,000 at its peak so they used 1,746 workers or machines, and then let me check. Yeah, the whole process takes about 845 seconds? No, 891 seconds. The second process, the second column, was used with no backup tasks. So as you can see, it finishes about all tasks at around the 850-second mark, but 5 tasks remain working because I don't know, that they were faulty, or the computers were failing, or something was happening that they were struggling. So the whole process didn't complete until all of those processes were completed. And as you can see, it's 44% more time to complete because no backups were assigned. And in the third column, the 200 tasks were killed intentionally several minutes into the computation to see what would happen and how much it would affect. And as you can see, it only took 933 seconds to complete the whole computation. So it's only about a 5% time increase. So as you can see, machine failures or task failures is not that big a hindrance because of how the master distributes all the work among the rest of the cluster. So yeah, Google has been using MapReduce. Well, it was written in February of 2003. And I mean, the use of MapReduce has grown exponentially in Google. And well, according to Google, it has provided several benefits because as you could see, the code is very, very simple and very small. And so yeah, Google uses it for production, large-scale machine learning problems, clustering problems, extraction of data, extraction of properties of web pages for new experiments, large-scale graph computations, data mining, all that sort of stuff. And obviously, there's a lot of stuff that MapReduce uses that is used in other programs or takes inspiration from other programs. But according to Google, at least, MapReduce is the most complete package for this kind of work. And another program such as bulk synchronous programming makes it easier for programmers to write parallel programs, but they're not automatic like MapReduce. Or there are other systems that use similar backup task mechanisms, but if one task has repeated failures, there's no way to skip that like MapReduce you can with the bad record skipping and that sort of stuff. So I don't know if you want to give a conclusion or.
No, I think that's it. You kind of cover the conclusions.
Yeah, I don't know if any of you guys have any questions.
Yes, I have one question.
Mm-hmm.
How do we ensure that, let's say, if one step fails, let's say if a map or a reduce step fails, and this work I can imagine that is rescheduled, how do you ensure that the input data is still available? Is this input data redundant, or how this is done in the MapReduce?
So the way it works is,
go ahead.
Well, the master is pinging the workers periodically, and if there's no response, the master marks the worker as failed. And the master has all the information. So the way that each worker works or completes their tasks, they use their local disks to complete the task. And once it's completed, they send it back to the master. So the master has all the initial tasks, but then there's no real bandwidth because all the work is done locally in each computer's disk. So that way, if it fails, the master just changes the status to idle again, and then reassigns the whole task to another worker. So there's redundancy that way.
I have another question. What happens if the master stops responding? Does the workers keep working until finish? And I don't know what happens there.
So you can it's very easy to make the master write periodic checkpoints of all the data structures. So if the master dies, a new copy can be started from the last checkpoint. But according to Google, they say that the master failure is highly unlikely And so the current implementation just aborts the whole computation if the master fails, and you can just start with a new master.
Right.
I have another question. What are the main configuration parameters that the user or I need, or yeah, that the user need to specify to run the map reduce?
Let me just try to go back to the. So I successfully run this one. And as you can see, basically the configuration is already given. So I can tell you which are the defaults, like how many workers or how many map workers or how many reduced workers will the algorithm do. Just in this case that I didn't provide anything, or the file size of the split items. But the idea for you is to, if you need to do so, you can provide that in configuration through this object. As you can see, I already set as default. Now, I actually thought about a scenario where you can establish, okay, I want to process. This is just a silly scenario, but it's just to highlight the problem. I want to process a petabyte file size, and I just want to use I just want to use 3 map workers and 1, reduce worker. So the files are stored locally in each of the computers, and one that we didn't mention but actually is on the paper is that the map reduce can work in common PCs, like PCs that regular users use it on a daily basis. So the storage would be, in this case, in this particular scenario, could be a problem because maybe you don't have the petabyte, size for all of those. So that would be a bad configuration on the programmer side. But it's not to highlight the problem, but also to think about which is the best configuration for your algorithm to run. So you can maybe, there's no mechanism nowadays on the MapReduce model that will tell you or will feedback you with the, hey, maybe you can increase or you can decrease the number of map workers or reduce workers in order, based on the logs of the previous executions. But that would be a really good enhancement that providing you with the best configuration for your algorithm or for your particular algorithm. Right now, it's just that you can configure, how many map workers do you want, how many reduced workers do you want, the file size, and if you want the backup task enabled or not, or if you want how many skipping records or how the percentage of the skipping records the bad records you will allow. So you can play with those, but there is no actual, best configuration for each algorithm.
Google recommends in the paper that the way you partition the map tasks, because every computer does it in their local disks, they recommend splitting them into 16 to 64 megabytes per file. So depending on how large your file size, you can just do a division and see how many tasks it would require. And that's the way the paper recommends it. But
yeah, and also there is another point about, you would like to have the processes for each of the nodes at 30% of the capacity, just to not become that computer straggler that, in time will execute all the tasks slowly or is, slower than it was before because of the performance issue.
In regards to the code, I don't remember the name of the utility you're using, Apache something. Is this open source?
Yeah, it's Apache, okay. So everything under Apache, it's an open source project, okay. Yeah.
if you
Actually, what I downloaded was the Hortonworks sandbox, and it's just a virtual box actually that use Docker containers to actually create the cluster. So another question that I had was on the paper. It mentions like static clusters, like you have 100 nodes or 1,000 nodes, but basically this idea or the MapReduce could actually be combined with the cloud, with a cloud infrastructure, so you can actually ask for more storage as you on demand, or more nodes. So that would be really cool to actually test. But I test with the sandbox of Hortonworks, but implements Apache Hadoop. So
question, if you go back to the performance graphs, in the
yeah.
shuffle phase, there's a time space where no data is being processed or transmitted. I think that's because our workers are busy, or why is that?
There is a transition phase. I mean, the shuffle phase, it will work as your very similar to the reduce. Actually, you can provide a shuffle or a combined function. The idea is just to take all the intermediate keys, then shuffle them to arrange them to be the same, because the idea is to have it. Try to have all the same key values, intermediate values on the same node, so there won't be any networking coming and going on the cluster. So if you have everything on your local storage, you will save up a lot of the networking. So if you can see here, probably it was the shufflers doing some work, then stop doing them, and then start shuffling again, because of the maybe not all of the reduced workers were on the same node, so they need to shuffle again.
Okay, so it's all about the cluster, right?
Yeah, and how the files are distributed, or how the intermediate keys are distributed across the different reduced workers.
Okay, got it.
Is there any more question?
Yeah, I have one quick question.
Go ahead.
Yep. So if for some reason a developer or the company don't go with this option, do you know if the other approach will be do the job by brute force, or do you happen to know any similar way to achieve this task? Any famous enhancement to this same MapReduce?
I'm not quite sure if I get the question, but I would say, I mean, during this course, of course, we're gonna see, not only MapReduce, but we also do, probably we will see, apart from Apache Hadoop, Spark, and other type of implementations. There is another one which is the Spencer or Stem. I don't remember the name, but yeah, there are a lot of other type of distributed systems that could probably do the same as the MapReduce. Now, of course, in the paper, Google says there are other options out there, but either they don't, they use a lot of the network bandwidth, or they don't are fault tolerance, or that it's kind of the MapReduce.
Yeah,
it has a lot of advantages.
Yeah, you have to program the whole parallelizing yourself, and that is, I don't know if you know how to do that. I don't, so.
Okay, yeah, thanks.
Yeah, they use Yarn, by the way, for parallelize all the tasks. So it's kind of like a module on the MapReduce. They use Yarn. Yeah, you would need to implement that by yourself instead of just using it as a MapReduce they already provided.
Yeah, the MapReduce library already does a lot of things behind the scenes. So all the inter-worker communication, the parallelizing, the distribution of work, the partitioning of the files, it does everything automatically. So I mean, it just saves a lot of work.
Okay, thanks.
More question? Okay, thank you guys. Thank you, Javier. Thank you, Roberto, for detailed presentation. Can you stop sharing? Okay, I just need to comment something here. I'm sorry, Robert, I'm going to be disappointing you. I'm not going to talk about Spark, Hadoop, Yarn, and all those similar things. But if there is anything better than MapReduce, I bet there are. I mean, in certain tasks, you can find maybe, I don't know, Yarn performs better, or in certain tasks, maybe Spark is performing better. But the whole idea here was MapReduce was the one that started all this basically massive data analysis. So we wanted to know how they did it, what was the basically core ideas behind their proposal. So let me show you something. So, okay, I don't know how many of you've seen this announcement. I hope you all have seen it. So I uploaded this presentation rubric. Come on. Okay. So this is the presentation rubric. So part of it is timing. I want, as I mentioned, like 20 to 30 minutes presentation. Of course, there are more time for question and answer. Then presentation style, slide style. On time, because I want you to email me the slide before the class, because again, if you, I don't know if you're checking this constantly or not, because the paper is ready here for you, their presentation, okay? So before we have the class, the student presentation is here ready. My presentation also is ready. Sorry, I forgot to do that. Okay, so you can check this here. That's why I want you to email me the slides, like the same that they did it. So there is this 4 randomly selected students. I'm going to ask them, and I'm going to do it now. So these are you. I'm going to see. I want to just be totally random. Okay, just to be. Jose Antonio.
Yep.
So can you tell me about what was the problem being solved in this paper?
Okay, so the problem was basically, well, as I understood, Google trying to solve big data issues, right? So if we have like a big amount of data in a document, I think it's mainly what they talk about. Basically, they part in several workers. So then all those workers, I mean, it will create a map, right? Separate. For example, in the second slide, they mentioned, right, the example of, I don't remember the things, but different things. So they processed all those things and create separate documents, right? Basically isolated by the type, I mean the key, and then the value will be the count, right? So that's the basic idea of this, right? Trying to solve this thing is trying to solve.
Okay, thank you, Antonio. Perfect, accurate answer. I'm going to pick another one. Hector Gabriel.
Yep.
So can you tell me the key inside of the paper?
Sure. Well, it's this is a framework for processing a large amount of data sets. And the system or the framework is usually composed of three operations, which is the map, shuffle, and reduce. In the map, let's say there is input data, which is splitted, and let's say there is a master node that ensures that there is only one copy of this redundant data input to be processed. And then there are another nodes that perform the jobs. And then the shuffle redistribute this data and let's say organizes the data belonging to a specific key or ID, if I remember correctly. And then the reduce step in which the nodes process each group of data to have a small amount of data with, let's say, the relationship as per the key. And all of these steps are performed in parallel.
Okay, perfect, thank you. Basically, what you did, you covered the third question.
Oh, sorry.
It's fine, never mind. It's perfectly fine. So I'm gonna go with the last one. Last unlucky student is so can you tell us about how this paper advanced the state of the art? Alejandra?
Sorry, yes, I was on mute.
Okay.
The paper advanced the states of the art. I don't understand the question. What do you mean?
I mean, how it started change. I mean, I mentioned it, like, but how it impacted the industry, let's say, the state of the art of data processing.
Well,
I know it's a little bit general question. Okay, it's just so there is no like perfect answer. No worries.
Well, as Javier mentioned it, like for example, Google that use this system. I mean, like you can solve like a lot of problems, like of I don't know, like we discussed like the timing of request and the answer, and I don't know how to explain it. Like I think that it helps a lot, like losing data, for example, or sort data. I think this is very helpful for a lot of companies. Like I told you, as Google, but I'm not very sure about the answers.
Okay, it's fine. Roberto, can you tell us?
What?
No, I'm asking Roberto, who presented the paper with Javier. So can you tell us what happened after, or like how this paper advanced the state of the art?
Well, probably, of course, when it comes to a large processing, well, the processing of large, or really big files, it would be really easy just to implement these programming model. Like if you're just, if you're just one guy and you're assigned, or the problem that you would like to address is actually process a lot of records. The main idea is for you to just use this MapReduce framework, and the framework will do everything for you, from the parallel computing to fault tolerance to keep a record, monitoring the task. Also, there's a debugging functionality available for you. So it kind of, you know, programming wise, it's kind of a powerful tool for you to use, and it's very simple to implement. As I tried on my local computer, but again, it took like, you know, 10 gigabytes of RAM out of the 16 that I have, and it took 4 cores out of the I don't know how many I have. I have like 12 cores probably, but again, it was, you know, it was really slow to have the presentation and the cluster working. But actually, I found it really easy to implement, and it is, you know, it's like having a powerful tool right there. You just need to use it.
Perfect. Thank you, Roberto. Thank you, Javier, for our presentation, for answering questions. It was great to me.
Thank you.
Yeah, we're done with today. Let me just